Since we've been spending so much time talking about concentration or solutions in this case, and aqueous solutions, it's important we understand the term concentration of a solution. Concentration refers to how much of a certain solute has been dissolved into a solution. And there are several ways we can measure concentration. In society or in general use around your household, you will probably see what are called percent concentrations. Percent concentrations are simply that. They describe something as a percentage composition. So for example, in your medicine cabinet, you might see 3% hydrogen peroxide, or you might see 71% isopropyl alcohol. Or you might see in alcoholic beverages and labels and advertising that it's 5% ethanol. What those percentages are simply telling you is just that. What percentage of this solution is made up? Now, generally speaking, the percentages are based on grams of solute per 100 grams of solution. So in a 3% hydrogen peroxide, that means there are 3 grams of hydrogen peroxide per every 100 grams of solution. So that means there's 3 grams of hydrogen peroxide, 97 grams of water, so to speak. Isopropyl alcohol, or things that exist in a liquid, are probably percent by volume. So 71% isopropyl alcohol means there are 71 milliliters of isopropyl alcohol and 29 milliliters of water mixed together. So it's sort of a watered down effect. In chemistry, most commonly we use a term called molarity. Molarity is defined as the moles of a solute per liter of solution. Now, when we're measuring molarity, you will see things called a 1 molar solution, or a 5 molar solution, or a 2.4 molar solution. What that's simply saying is, if I have a 1 molar solution of something, let's say I have a 1 molar copper chloride solution, all that is telling me is that I've taken 1 mole of copper chloride and I've dissolved it in enough water to make 1 liter of solution with the water and the solute combined. So we say that's 1 molar, and we use a capital M to designate molarity. So the word concentration and molarity you need to see as interchangeable. So if you're asked for a concentration, you're being asked for the molarity. If you're asked for molarity, you're asked for the concentration. Now let's look at an example of how we would go about calculating such a solution. In our first example, we're asked to calculate the molarity of a solution made by dissolving 23.4 grams of sodium sulfate in enough water to form 125 milliliters of solution. Now, again, molarity is concentration. So we're asked to calculate molarity, so we need to know moles of solute over liters of solution. In this problem, we're not given either of those two numbers. We are given grams of solute, and we're given milliliters of solution. To get liters of solution, we can simply move the decimal and know we have 0.125 liters of solution when we're done. To get moles, we're going to do what we learned in Chapter 3. We'll take our 23.4 grams of sodium sulfate, and we're going to multiply by 1 over the molar mass. So we have to figure out the molar mass beforehand. So on our calculator, we simply punch in 2 sodiums, which are 23 each, so that's 46. 2 times 23 is 46, plus 32.1 for sulfur, plus 4 times 16 for oxygen, which is 64, giving us a molar mass of 142.1 grams. So, using our calculator now, if I take 23.4 and I divide that by 142.1, I get 0.16467 extending moles. Because I'm giving 3 sig figs here, I have to round up to 3 significant figures, and I say I have 0.165 moles of sodium sulfate. Now, to figure out the molarity, what I need to do next is I take my numbers I'm given, 0.165 divided by my volume, 0.125, and I get a molarity of 1.32. So we say we have a 1.32 molar sodium sulfate solution. All right, let's look at another example. How many grams of potassium dichromate are required to prepare a 250 milliliter solution whose concentration is 2.16 molar? All right, so we're going to make a solution of potassium dichromate, and we need to make 250 milliliters of it, and we want it to be 2.16 molar. So we need to calculate how many grams we need. So again, we start with the molarity equation. Molarity equals moles over liters. We plug in what we know. 2.16 is the molarity. 0.250 is the volume. And we can't find grams, but we can find moles. And once we find moles, we can figure out grams. So mathematically speaking, we bring back our calculator again. We take 2.16 times 0.250, and we get 0.54 moles are needed. Since we know 0.54 moles, in order to go from moles to grams, we need to multiply by the molar mass. But first, we need to know the formula for potassium dichromate. Potassium is K, that's +1. Dichromate is Cr2O7 -2. So therefore, K2Cr2O7 is our formula for potassium dichromate. So again, we need to add up our molar mass. Two potassiums, if I look at my periodic table, I see potassium is 39.1. So 39.1 times 2 equals, oh, didn't clear everything, 39.1 times 2 equals 78.2, plus 2 chromiums. Chromium from your periodic table is 52, so that's 104, plus 7 oxygens. 7 oxygens, 7 times 16, comes out to be 112. So we add all those up, and we get a molar mass of 216 grams per mole. So now that we know that, we can take 0.514 times 216 grams per 1 mole. And we find that we need 120, rounding to 2 sig figs, actually 116, sorry, rounding to 3 sig figs, 117, 117 grams of K2Cr2O7 would be needed. All right, so calculating molarity is an easy thing to do. It's a simple, what I call plug and chug kind of problem. You take the equation given and you solve for what you need. We just learned how to talk about how to calculate concentration of solutions. But what we're going to look at here is then sometimes we're not concerned with the whole solution. We're only concerned about a specific ion in solution. So once the solution has been made, we need to figure out what the concentration of a specific ion might be in that solution. When ionic compounds dissolve, we know that they do dissociate into ions in solution. So for example, a 1 molar sodium chloride solution has sodium gone in there. So since I had 1 mole of sodium chloride going in, I have 1 mole of sodium in solution, I have 1 mole of chloride in solution. So my concentration of my 2 ions would be 1 molar sodium ions and 1 molar chloride ions. Sodium sulfate, however, has a different perspective. If I take a 1 molar sodium sulfate solution and I dissolve that in water, when it breaks apart, sodium sulfate is going to generate 2 particles of sodium for every 1 sulfate. So if I have 1 mole's worth, or 6.02 times 10 to the 23rd particles of sodium sulfate, I have 1 mole. When I put that in, it's going to break apart. And for every 1 of these, I'm going to generate 2 times that number sodium ions, and I'm going to still have that number of sulfate ions. So when we talk about ion concentration, the way you get an ion's concentration is you take the number of a specific ion in a formula times the overall concentration of the solution. Now let's look at another example of that. If I have a calcium nitrate solution, the first thing I have to do is figure out what calcium nitrate is. Calcium is Ca, and from the periodic table we know that's +2. Nitrate is NO3, and from my polyatomic ion list I know that's -1, giving me a formula of CaNO3 2. Since it's an ionic compound, we know for sure that ionic compounds will dissociate. So when I put that in water, if I have a 0.25 molar solution of calcium nitrate, I want to know what the concentration of each ion would be in solution. The way I figure that out again is I take the number of each ion in the formula times the concentration. So calcium since I have one of them, would be 0.25 molar. Nitrate, though, has 2 ions in it in the formula. So to get nitrate ion concentration, we would simply multiply by 2 and we get 0.50 molar nitrate ion concentration. All right, so expressing ion concentration is very simple, but it's a very important concept to be able to do. The last thing we're going to look at in this section is diluting a solution. Sometimes we get solutions that are already made stock form in concentrations. Acid, for example, when we buy acid, is already made in solution. Therefore, preparing a solution from another solution is different than preparing a solution from a solid particle. When you prepare a solution that already exists, we have to dilute it or water it down. And that's a term you should be familiar with, dilution. In order to figure out what is needed, we have a very simple formula, and the formula is MIVI equals MFVF. MI refers to the initial concentration of the solution you're starting out with, or your stock solution. VI stands for how much of that initial solution you're going to need. MF stands for what concentration do you want to obtain at the end, and remember, MF always has to be less than MI because you're watering it down, it's going to have a lower concentration. And VF refers to the final volume of solution you want to have. So let's look at an example of this. It's a very simple concept to get. How many milliliters of 3.0 molar sulfuric acid are required to make 450 milliliters of 0.10 molar sulfuric acid? All right, so let's say in my example here, I'm preparing a lab, and for the lab I need 450 milliliters of 0.10 molar sulfuric acid solution. I look around on my shelves and I don't find any of that solution, but I do find that I have some 3 molar sulfuric acid. So I can make that solution up by watering some of it down. My question is, how much of that 3 molar sulfuric acid do I have to start with before I start adding water to it to make it 450 milliliters and get my 0.1 molar? Well, it's sort of plug and chug kind of, if you will. MIVI equals MFVF. All right, so what is my original concentration? My original concentration of solution is 3.0 molar, so that is my original molarity. VI is what I'm trying to find. I don't know how much of that original substance I need, so I leave that as is. MF is what's the molarity of my solution that I want it to be, 0.10 molar sulfuric acid. VF is how much do I want to have at the end. I want to have 450 milliliters of solution in the end. Now it's important to understand that in this problem, when you are given VI and VF, if they are not in the same units, they must be put in the same units. VI in this case, since I'm solving for a volume and I'm given another volume, whatever unit VF is in will be the unit VI will be in when I solve for it. So mathematically then, we get 0.45 equals 3.0 VI. So VI equals 15 milliliters. So in order to make this solution, I would have to take 15 milliliters of my original solution, and I would have to add to that 435 milliliters of water to water it down to make my solution. All right, so these are pretty simple problems, pretty straightforward, and there's really not much complexity to them that you can't figure out.